So without further ado, because we have each presentation is going to last for 20 minutes, I need to get off and introduce my colleague, Dr. Zoe Milden from the University of Plymouth, who's going to give us a presentation for the next 20 minutes on earthquake impacts. So over to you, Zoe.
Thank you, Greg. Good morning.
Pleasure.
Good morning, everybody in virtual space. So yeah, so as Greg said, I'm going to talk primarily about earthquakes and the effects that earthquakes have on the world, or in tectonically active areas. And I'll talk a little bit about, I'm also going to talk a little bit about how do we actually prepare for earthquakes towards the end of the talk. So what I'm going to start off with, though, is I'm going to ask, what is it that actually causes earthquakes? So what I'd like you to do is either get a smartphone, or if you're on a laptop, open up a new tab. And I'd like you to go to www.menti.com, and I'll put this link in the chat as well. And this is going to be, in case you haven't used Mentimeter before, it is going to be a word cloud. And what I would like you to put in is what you think it is that causes earthquakes. So I've just put the link and the code in the chat. So what is it that causes earthquakes? And I'm really interested to see what your thoughts are on this as a starting point for my talk today. And staff and other speakers, if you want to join in as well, please feel free. So I'm going to switch sharing my screen. I'm going to show the word cloud. I can already see that some people are putting in answers, which is excellent. So the bigger the words, the more people that are putting in the same answers. So this is great. I'm seeing lots of tectonic. I'm really pleased that tectonic activity is coming up as the very biggest one. We've got plates, faults, friction. Excellent. Stress, humans. Oh, that's actually really interesting that somebody has put humans in there. That's not something that I'm going to really touch on today, but humans causing earthquakes can be a really big challenge when it comes to communicating and talking about earthquakes. But I'm glad to see that the geologically important ones like friction, tectonic activity, tectonic plates, these are the ones that are coming up the biggest. So that's the most people putting those in. So that is good to hear, good to know. So I'm going to go back to the PowerPoint, my presentation, because clearly we've all got quite a good idea of what it is that actually causes earthquakes in terms of the geology. But this isn't always the case. So if we were to go back to ancient Japan and ask them what is it that causes earthquakes, they believe that earthquakes were caused by a giant catfish called Onamazu, who lived underneath Japan. So Japan kind of sat on its back, and the catfish would normally sit still, but because it's a catfish, it can't always sit still. So occasionally it has to give a little wriggle, and those wriggles are what caused earthquakes, according to the ancient Japanese. Now, obviously, we know that that is no longer the case, or that's not the case. Instead, we know that earthquakes are caused by movement on faults. And so this is a photograph of a road cutting actually in the US. This is in the Moab fault zone. And what you can see is that these colored layers within the rocks are all offset from each other. And these offsets are caused by faults. So each one of these little steps that we see in the color would have been generated by an earthquake or a series of earthquakes. Something else that was picked up quite nicely in that word cloud is that lots of you put in tectonic plates as causing earthquakes. And if we look at where are earthquakes on Earth, which is what's shown in this diagram here, where they're color coded according to their depth. So the red colors are shallow earthquakes, whereas the yellows, greens, and blues are deeper earthquakes within the Earth. And we can see that earthquakes aren't distributed evenly around the globe. They're concentrated generally into quite narrow zones. And these narrow zones broadly align with the edges of tectonic plates. And this theory of plate tectonics was first developed, it was really developed in sort of the 50s and the 60s. And this tells us the broad patterns of where earthquakes do and don't occur on the Earth. There's always a few exceptions to this. So, for example, here in the UK, we're obviously quite a long way from a tectonic plate boundary, but we do experience some earthquakes. And the other thing that plate tectonics tells us is not only does it divide the surface of the Earth up into kind of jigsaw pieces of the crust, but each of these boundaries between those jigsaw pieces, between those tectonic plates, gives us slightly different types of earthquakes. And there are three key types of earthquakes, which I'm going to just run over. So the first type of earthquakes and faults are strike-slip faults. So these are where the crust or the rocks slides past each other in a sort of translational way, which is what's shown in this animation here. So the ground level stays the same, and it's just that the plates are sliding past each other. And probably the most famous strike-slip fault system and tectonic plate boundary is the San Andreas Fault, which is in California, which is what's shown in this picture here. And you can see that there's a river channel through here, and then all of a sudden the river channel jumps. And that jump, that offset in the river channel, tells us about where the fault is. There's another example over here on the right-hand side. This is me standing there for scale. And this is after an earthquake in Japan in 2016. And you can see that this yellow line across the road is offset because it's been pulled apart by this strike-slip earthquake. The second type of faults and earthquakes are normal faulting earthquakes. So these are faults that accommodate extension. So, for example, plates pulling apart from each other. And these faults, I've already shown you one example of this. So this is the Moab Fault in Utah, and in this you can see that the rocks are being offset vertically from each other. So normal faults includes vertical movement, whereas strike-slip faults are just side-by-side movement. Another example of a normal fault is the Amatrice earthquake in central Italy in 2016. So in this photograph, I hope you can all see that there's this a pale stripe that comes along the base of this kind of grey rock surface. Now, what that pale white stripe is that is where the grey rocks at the back of the background of the picture have been moved up as a result of the earthquake, whereas the grassy slope in front has moved down because of that earthquake, and has so exposed that extra bit of rock during the earthquake. And then the final type of earthquakes and faults is reverse faults, or sorry about that, also called thrust faults. And this is where you've got two tectonic plates coming together, and rocks are being pushed on top of each other. So some examples of this are Kobe earthquake in Japan in 1995. Again, this is me for scale, and this is in a museum in Japan where they've actually dug across the fault that caused the earthquake in 1995. And you can see that this side of the ground, and this is the ground that they've preserved by pumping loads of like glue and things into the actual soil. But you can see that this side of the ground has gone up, and the other side has gone down. Another really famous example is the Chi-Chi earthquake in Taiwan in 1999. And you can see that the back of this picture, so this is a running track, the back of the picture has gone up and the front of the picture has gone down. Now, this last one is actually a really nice illustration of what one of the hazards of earthquakes, and that is that earthquakes can cause the ground to actually to be broken and to change in its shape. And that can be a real problem if we've got important infrastructure that runs across these faults. A running track is maybe not very important infrastructure, but imagine that that was a pipeline for gas or for water, or imagine that was a bridge. And you can see that that offset in the ground surface is could cause potentially quite a bit of damage and hazard as a result of the earthquake. But normally when we think about earthquake hazards, we also think about ground shaking. So the actual, rather than just the ground being offset, the ground shaking due to seismic waves. And the way that we look at these seismic waves is we use something called a seismometer, which measures how much the ground moves during an earthquake. And this is a video which is going to show you, it's an animation of an earthquake that's going to start somewhere around the center of this picture. And what you're going to see is the seismic waves spreading out as recorded by seismograms. So I will play this through. That's up there. So you can see these rings of blue and red. So the red is where the ground has moved up, and the blue is where the ground has moved down. And you can see that these look a little bit like rings. If you imagine throwing a pebble into a pond, they look a little bit like the waves that will be generated on that. And seismic waves are very, very similar to that. And this seismogram down the bottom here, this shows what you would actually record at a single seismometer, so the ground motion at a single point that goes into kind of making up this animation. And seismic waves are commonly split into three different types. And some of these names may be familiar to you. So we have the P wave, which is the P stands for pressure or primary, and this is always the first wave that arrives. We then have the S wave, which is called the shear or the secondary wave, which arrives a little bit later. And then finally, we have the surface waves, which arrive even after the S waves. And it's these surface waves that are typically the most damaging. But what I'm going to talk about now is this question that, as an earthquake researcher, I get asked pretty frequently of, can we actually predict earthquakes? Because what it seems from our observations is that earthquakes tend to be quite chaotic and unpredictable. But we can go and have a look at the model of plate tectonics and get an idea of which areas are at risk. But doing precise prediction, by which I mean there will be a magnitude 8 earthquake tomorrow at this location at this time, that has so far proved impossible. We simply cannot do that. But there are some other types of prediction that I'm going to run through. So one is long-term prediction, which is sometimes called forecasting. And the other is short-term prediction. So by long-term, I mean many, many years. Short-term, I mean sort of hours to days. So the long-term forecasting typically takes the form of things like this is a probabilistic seismic hazard map for the whole world, where the reds and the oranges are the areas where there are highest seismic hazard. The whites and the greens are where there are lower seismic hazard. And you might be spotting that the plate tectonic boundaries are put onto here, are put on this map. And you might also remember that there are things like the subduction zone along South America. We've got the subduction zone along Japan. And then the San Andreas fault system is up here in Western US. And it's these edges of these tectonic plates which typically have the highest hazard. Now, this is most commonly used by engineers. It's not that useful for people on the ground, because the way that this is expressed, the units of this map are not very intuitive for people that live in these areas to understand. So this kind of information is really useful for engineers, and I'll come on to why engineers need to know this in a minute. Thinking now about slightly more shorter term forecasting, there is a technique that we can use called Coulomb stress transfer, because the sort of general view is that when an earthquake happens, that's releasing stress that's built up in the crust. And that's something that came up in the word cloud. But actually, it's not that simple. Actually, an earthquake changes the state of stress in the surrounding rocks. So in some areas, the stress decreases, which is what's shown in blue in these pictures. But in other areas, the stress increases, which is what's shown in red. And the best example of this acting as a forecast is if we look at the North Anatolian Fault in Turkey, which is a strike-slip fault system. And what we saw, or what we see, is that there is a very clear progression from the east to the west of earthquakes from 1939 to 1992. And this paper was published in 1997. And the authors said that the next area to have an earthquake will be this region here, this bright red region, which is the area of Izmit. We don't know when it's going to happen, but this is going to be the area. And if you know anything about your earthquake history, in 1999 there indeed was an earthquake in the area of Izmit, which was exactly the location that was predicted. But as I said, we couldn't. The authors, the scientists that did this study, didn't have any idea of when it was going to be. Most fault systems around the world are not as simple as the North Anatolian Fault. So we don't have many other good examples of exactly this type of forecasting. I'm now going to focus a little bit on a short-term forecast, and this is animal behavior. And this again is something that I get asked quite often about. Can't animals predict earthquakes? And I'm going to show you this video, and I'm going to just change my screen sharing back to something else. And I'm going to play you through this video. And what you're going to see is you're going to see a dog reacting to the earthquake, or reacting to an earthquake. So the dog's just sitting there. And then all of a sudden, it gets up and runs. And then a few seconds later, the whole room starts shaking. So this is sort of an example of what this could lead people to think, that dog predicted the earthquake. Actually, what probably happened is that notice that the dog is sitting down, so it's on the ground. What's probably happened is that the dog actually detected or felt the P waves, those initial small waves from the earthquake, reacted to that, but the humans didn't notice it. So they only noticed it when the surface waves, so the big shaking, happened in the video. Okay, so if we can't predict earthquakes, then what we need to do is we need to try and prepare for them to happen. And there are many different ways we can do this. So, for example, countries can develop building codes. And this relates back to the probabilistic seismic hazard map that I talked about before. Countries can also have earthquake early warning systems, or countries can develop education programs to make the program aware of the hazards and what to do in an earthquake. So developing building codes is really important because most deaths in earthquakes are caused by crushing or falling masonry. There's a saying that it's not earthquakes that kill people, buildings do. So this is a photograph of a building in central Italy after an earthquake in 2016. And just to illustrate the difference between this scenario, where you can quite clearly see that the roof has collapsed. This is a video that was taken of a slightly different earthquake, but still in the same region. And this is a video taken by a group of hunters that were out in the countryside. So you can hear them saying, "Oco Dio, oh my goodness, oh my God." And you can see that the ground is shaking and all the trees and so on are shaking. I won't play the whole video, but those hunters were absolutely fine. I mean, they were almost certainly shaken up, but they were fine compared to that previous building. We also have, as I said, countries can also use earthquake early warning systems, and they work using some of the key principles of seismic waves. So as I said before, we have these three types of seismic waves: P waves, S waves, and surface waves. Now, the P waves and S waves, they're not very damaging because the amount of movement that those generate in the ground is pretty small. So these wiggles on this seismogram are quite small. However, the surface waves are very, very damaging. And those are the ones that cause these are the ones that cause the vast majority of the damage. But you can see that there's a time delay between the P waves arriving and the surface waves beginning. And the speed of these seismic waves is much, much lower than the speed that we can send data via the internet or via cables. So for the way that we can then use this is we can say, if there are seismometers that measure those initial P waves, we can then use computers and modeling to predict how big the surface waves are going to be and when they are going to arrive. So this is a video of how the earthquake early warning system actually works in Japan. So this is a video taken in somebody's apartment in Tokyo, which was during the 2011 Tohoku earthquake, about 400 or 500 kilometers further north. So you can hear the countdown. If you know Japanese, it's a countdown of numbers, but if you don't know, they are. And you can see that there's a little bit of shaking, but not very much. And it's going to get stronger, but it's get more intense in just a moment. The stopped, and the amount of shaking increased on the video as well. You can hear things moving around in that apartment. Early warning systems, they can give between seconds and tens of seconds advance warning of those damaging earthquakes, those damaging waves arriving. Now, you might think that tens of seconds, I mean, that example was 30 seconds. You might think, oh, well, what can I do in 30 seconds? But actually, there's a lot that can be done. So, for example, in Japan, they have these very, very high-speed trains. And if they get those seconds of warning, they can automatically slow down those trains and try or stop them to avoid them being derailed during the shaking. You can also stop surgeries. So, for example, if you're in a hospital having an operation, you probably don't want to be having a surgeon operating on you when the ground is all shaking and their hand is shaking. That would probably not go very well. You can also do things like shut down manufacturing plants, nuclear power stations, those kind of things. But also, it gives people the chance to prepare. So I'm going to ask you another question. So if there was an earthquake right now, wherever you are, what would you do? So if you go back to the Mentimeter link that I gave before, that was also I put it in the chat. And this is going to give you a multiple choice. This should give you a multiple choice option. So you've got 5 choices. If there was an earthquake now, would you run outside? Would you panic? Would you stand under a doorway? Would you hide under a table? Or would you do nothing? So these are the results as they're coming in. I'm not surprised that a couple of you have said panic or do nothing. It's a fairly common reaction if you've not been in an earthquake before. I'm quite glad to see that there's a number of you that said hide under a table, and that will become apparent in a minute. The run outside, I'm not surprised that so many of you have voted on this. The challenge is that if you try and run outside when that shaking hits, how fast can you run when the ground is moving underneath you? Because then if you try and go outside and you fall over and let's say break a leg or hurt yourself, you've then got to wait for somebody's then got to come and rescue you. So actually the advice is almost never to run outside. But going back to the hiding under a table, as I said, I'm quite glad that so many of you have put that as an option. I'm going to show you a video here of, this is an earthquake which happened in Alaska. And this is in a classroom setting.
Don't let yourself be convinced to do something that you know is bad. And then
So you can see the shaking starts. And everybody gets under the tables pretty quickly. As you can see, that's obviously these students clearly were practiced. They knew exactly what to do. In the same way we do fire drills at schools and workplaces, other places do earthquake drills. And while getting under a table may not save you if your entire roof collapses. What if this further on in the video, you see like roof tiles start falling out of the ceiling tiles start falling out of the ceiling. And it's those kind of things that you can protect yourself from if you follow the very simple steps of drop, cover, and hold on. So get under a table or whatever, or some sort of sturdy piece of furniture, and that can genuinely save lives. And this is the most common and best advice if you are ever in an earthquake, if you go on holiday, traveling somewhere that's earthquake prone when we're allowed to travel. This is the best advice to remember. So yeah, so to summarize, I started off by talking about what the different types of faults are and what they're caused by. But then most of the time I talked about why is it that we can't really predict earthquakes, and ultimately what can we do about them, both in terms of what can we do as individuals, but also what can we do what can countries and governments do in order to mitigate the effects. Because I don't think we're ever going to be able to predict earthquakes. We're never going to be able to stop them. So what we have to do and what we can focus on is actually preparing for them. So thank you very much, and happy to answer any questions.
Thank you very much, Zoe. Well done, brilliant. We're obviously, because I used up 5 minutes of your time, running a few minutes over. But
You did, I'll forgive you.
Any short questions before Josh takes over, we would welcome those from the floor at this point in time. So fire away, don't be shy. We can always come back to questions for Zoe's talk later on in the day as well. I
can also continue to answer questions in the chat as well.
Yeah, as time progresses, that's right. That's right.
Yeah. Oh, now I was very pleased to see that the majority of people said they would hide under a table in that last poll on earthquakes, on what would you do in an earthquake. So that's really good. Definitely the right thing to do.
I have to admit that I wrote in the first Menti chat humans as earthquake
oh, was that
agents.
You?
Well, there was two, so it wasn't just me. It was somebody else from the floor, but it was me as well.
That's very brave of you to admit, Greg.
Well, I didn't know if that was the right answer or not. That was all.
Well, okay, humans do cause some earthquakes, but they're probably more likely to be small earthquakes.
Right. Okay. Then.
For example, like fracking, for example, causes earthquakes, or geothermal mining. They all cause earthquakes, but they're much small. They're quite small.
Yes, certainly smaller than what you've been talking about, but highly controversial, I suppose.
Absolutely.
Earthquakes via fracking.
Absolutely.
Well,
yes.
We are just 4 minutes past the hour, so without further ado, we'll move on to the next presentation, and that presentation is by Josh, who is hello, Josh. Glad to see you here. Josh is studying for a doctorate at the University of East Anglia, but is actually based at the University of Plymouth. And Josh is going to be talking about landslidings. Here we are. Quick question before I get on to Josh, just whilst he's loading up the screen. Question to Zoe: what can be done about inequitable access to the technology which allows prediction of earthquakes? So that's to Zoe. Great question.
It's a really good question. Well, so there's a couple of challenges with the earthquake early warning system. So one is technology, as you've said that yeah, you need to actually have the infrastructure, and that isn't cheap necessarily. So some countries, the countries that have the best earthquake early warning systems are Japan, the US, Mexico are the sort of the most developed systems, and all those countries clearly have quite a bit of money. There's also problems with the earthquake early warning systems, that you also need the right geological setting. So you actually need the distance between the faults that, or the tectonic plates that cause boundaries that cause the earthquakes, and the people, because you need to have a distance between the two, because then that is what allows the time difference between the P waves and the surface waves, and therefore allows that communication to happen. So for example, in central Italy, where I do quite a bit of my my research, the faults, people live basically on top of the faults. So the P waves and the surface waves will arrive in pretty quick succession, a few seconds. So there wouldn't be the chance to have an earthquake early warning system in Italy, because they're just, geologically isn't the time. On the technology side, more developed countries can fund and support less developed countries to develop those kind of technological systems, or countries can choose to invest in education, which is relatively cheaper to do, and focus on what can individual citizens do rather than what can a government as a whole do.
Great, thank you, Zoe. Right, brilliant. We'll now move on back to Josh. So Josh is going to talk about landslides in the Himalayas. So Josh, the floor is yours.
Yes, great, thanks Greg. Yeah, so hi all, my name is Josh, and as Greg said, I'm a PhD researcher at the universities of East Anglia and Plymouth. And my research very much focuses on landslide processes and hazard in the Himalayas, which is what I'll be talking about today with this presentation titled Geology in Motion, Catastrophic Landslides in the Greater Himalayas. So in terms of the talk contents, I'll start by giving a kind of very brief outline of some kind of key landslide principles, including a description of landslide types, global landslide impacts, and some explanation as to why landslides can be very hazardous. To showcase some of those approaches, principles, I'll then talk you through two case studies of landslide events in the Greater Himalayas that have had very catastrophic consequences, and some of the lessons that we can learn from these events in terms of managing landslide hazard and risk. So first off, what actually is a landslide? Well, a landslide is a very, very generic term actually used to describe any mass movement, where a mass movement can be defined as any downslope movement of earth material due to gravity. So the word landslide is actually a very broad term that can include many different types of process. For example, this graphic shows the kind of main end member types of landslides that geologists will typically talk about. And you can see that these range from very different flow events to slides to topples and falls. So the word landslide is very broad. And furthermore, whilst often geologists could be tempted to classify landslides into just one of these types, in reality, a given landslide event will probably include a variety of these different processes. And this is already to highlight basically that the word landslide is quite broad and includes many different types of process. So this diagram shows the key anatomy of a landslide. I don't want to go into too much detail here, but I do want to mention a few key terms that I'll be using throughout the rest of this talk, which are the source zone, runout zone, and deposition zones of a landslide. Now, these are the main kind of three zones that exist within any landslide event. The source zone, as highlighted here, is the location where the the material involved in the landslide has originated. The runout zone is the path that material will have traveled downslope, and the deposition zone is where that material will end up being deposited. And I'll be using all of these terms throughout the rest of this talk. So I'm now going to move on to landslide impacts. So what are the impacts of landslides and why should we care about trying to manage them? Well, firstly, landslide impacts are very expensive, with an estimated cost of around $20 billion globally. This is clearly a significant amount, particularly given that much of this cost is incurred in developing countries, that are least capable of dealing with that cost. Furthermore, between 2004 and 2010, it's estimated that at least 2,600 individual landslides caused at least one fatality. And between 2004 and 2016, it's estimated that somewhere in the region of 56,000 people were killed by landslides. So clearly, both the economic and human cost of landslides is very significant, suggesting that we really need to do better at managing landslide hazard. And this leads to the question of, well, why are landslides so hazardous? There are many reasons that make landslides hazardous, and I'm going to go through a few of those now. First off, landslides can be absolutely massive. This figure shows the size distributions of several differently triggered landslides in various places from around the world. Now, don't worry too much about understanding this figure. The key thing to note is the x-axis, the bottom axis, which shows the areas that some of these landslides have covered. Now, this value here, this 10 to the 0, indicates that some landslides are up to 1 kilometer squared in size. Now, for reference, 1 kilometer squared is roughly 14 football pitches. So if you imagine 14 football pitches worth of earth and rock collapsing towards you, you'll get some idea of just how huge some landslides can be. The second reason that landslides can be hazardous is their mobility. Landslides can travel very quickly and move very large distances, which, as we'll see in some of the examples later, makes landslides very hard to avoid. The third reason is something called hazard cascades. Landslides very commonly induce other hazards, such as floods and tsunamis. So often when we talk about managing landslide hazard, we also have to consider managing a host of other issues and problems. And the final reason I want to mention is something called stochasticity. Now, stochasticity is a word that just kind of means random behavior. There's a lot of the landslide science community that consider a lot of landslide processes to be quite random. In particular, the triggering of landslides is often quite difficult to deal with. Sometimes landslides can be triggered by events we can forecast, such as rainfall. But sometimes they're triggered by events such as earthquakes, which, as Zoe outlined just now, earthquakes are very hard to predict. So landslides associated with earthquakes can be very difficult to predict and thus manage. And furthermore, often landslides sometimes occur seemingly without being triggered by anything at all. They just fail almost randomly. And this just makes landslide hazard very difficult to deal with and very difficult to manage. So all of these reasons make landslides a major geohazard. To illustrate this, I'm now going to take you through two examples of catastrophic landslides that have occurred in the Greater Himalayas. And in each case, I'll outline what happens in those events and some of the lessons that can be learned in terms of landslide hazard management. So the first case study is of an event called the Langtang Rock Avalanche. Now, Langtang is a region in the Greater Himalayas of northern Nepal. Now, at this point, I should probably clarify that the Greater Himalayas is defined as kind of the most northern part of the Himalayan mountain chain, where you get mountains sort of 6,000 meters plus. Pretty much the zone of red on this figure here is where the Greater Himalayas would be. And Nepal is a country pretty much completely in the Himalayas, wedged between India and China. So Langtang is a national park in Nepal, in the Greater Himalayas. It's a very beautiful place. It's got a fairly small local population, but it's very, very popular with trekkers and tourists. So that gives you some context as to what and where Langtang is. But what was the Langtang Rock Avalanche? Well, as some of you might remember, on the 25th of April in 2015, a huge 7.8 magnitude earthquake called the Gorkha earthquake hit central Nepal. Now, this event had some pretty destructive consequences. And one of those was that the shaking or ground motion caused by this earthquake triggered over 24,000 co-seismic or earthquake triggered landslides. And one of these was the Langtang Rock Avalanche. So I'm now going to talk you through exactly how this avalanche event unfolded. This is a satellite image showing the northern side of Langtang Valley before the earthquake occurred. And there are two things I want to highlight in this image. First, which is quite hard to see, but is where this red dot is, there is actually a town called Langtang Town, which was home to several hundred people. The second thing I want to note is that above the town, where I've put these red dots, is a hanging glacier. So a glacier that is slightly overhanging the main part of the side of the valley. Now, I'm now going to move to an image after the event to show you the difference between the two. So this is before the event, this is after the event. And you can see there's clearly been a significant change in the landscape. And what's essentially happened here is that the hanging glacier in this image completely collapsed during the earthquake. The shaking of the earthquake caused that glacier to collapse. The collapsing glacier then caused the underlying bedrock in this region highlighted to catastrophically fail, causing this huge avalanche of both rock, ice, and snow. Now, this photo shows you a kind of ground eye view of this part of the slope. This is a photo I took back in 2018. And this hopefully gives you some idea of how big the source zone, so where the material originated, the source zone of this event, is absolutely massive, way over 1 kilometer tall, half a kilometer wide, and a good 200 meters thick of rock that collapsed in this event. And we can also see, I've highlighted here the deposition zone of this event, so where this material ended up. And sadly, you can see that much of that deposition zone has completely covered Langtang town. I'll give you some context for how much material landed on the town. These deposits have been estimated to have a volume of between 5 and 10 million cubic meters, which for context is roughly the amount of volume of 1 to 2 Wembley stadiums. So if you imagine 2 Wembley stadiums filled to the complete top of the stands with rock, that's how much material collapsed in this event. So this is very much a textbook example of how a very large landslide has had some absolutely catastrophic consequences. So in terms of the specific consequences or impacts of this event, sadly, over 200 people were killed, mostly in that town, and hundreds more people lost their homes and livelihoods. This is another photo from after the event, showing one of the only buildings of this town that actually survived. The avalanche also had huge environmental impacts at some quite large distances from where the event actually occurred, further down the valley. Now, this photo looks weird, but actually shows trees that have been completely blasted down by the air wave that this avalanche triggered. And it's actually been estimated that this event caused a blast wave with energy equivalent to roughly 50% of the Hiroshima nuclear bomb. So huge amounts of energy were released by this avalanche. It's also estimated that the kind of falling rock had an impact velocity, so kind of velocity at which the rock hit the valley floor, around 99 meters per second, which for context is about 200 miles per hour or the top speed of a Formula 1 car. So again, going back to the slide on what makes landslides hazardous, an event that is both this big and this fast, this mobile, is pretty much impossible to avoid once it's begun. So all the lessons that we can learn from this event, well, for me, the key thing this highlights is the need to identify portions of the landscape with the potential for these types of hazards. So events of this scale, like I say, can't be mitigated. No wall is ever going to stop an event that's this big. So we need to know where landslides like this are likely to occur so that we can try to avoid them. Now, this typically involves developing what we call susceptibility maps, such as the one on the screen here that I've modeled for this region. Now, these maps essentially show which parts of a landscape are most likely to experience a future landslide based on landslides that have occurred in the past. And once these regions are identified, we can then begin to think about avoiding the hazard. Now, avoiding the hazard is actually very, very difficult. There are many social, historical, and cultural reasons why people live and work where they do, and it is highly unproductive for us as Western scientists to march into another country and start telling people where they should and shouldn't live. However, when scientists engage and interact with local people, it can be possible to make steps towards avoiding these hazards. For example, since the earthquake, a lot of engagement between scientists, government, and the local community led to many people rebuilding and relocating further up the valley. So the white dot on this figure to the left shows where Langtang town was located in this zone of very high likelihood of getting a landslide. The dot on the right, Tianjin, is the town that a lot of people have moved to, which, as you can see, is somewhat lower risk. So hopefully by trying to identify these hazards and then trying to avoid them, in the future, locals and tourists should be less at risk from a similar future event. Okay, so I'm now going to move on to my second case study, which is the very recent Uttarakhand disaster. Now, Uttarakhand is a region in northern India, shown here. So as you can see, it's pretty much directly west of Nepal, still located in that higher or greater Himalayas zone. The specific region impacted was the Rishiganga Valley, which is located roughly where this black arrow is pointing. So what was the Uttarakhand disaster? Well, some of you might remember this. This year, on the 7th of February, a sudden flood struck the Rishiganga Valley. This image is a freeze frame from one of the videos taken from this event. And what you can essentially see in this image is a huge flood surge charging down this valley. You can see the surge is full of debris and rock. And you can see if you look at the base of the river here, where my mouse is flicking, this surge is significantly higher than the usual level of the river. Now, this flood surge had some significant impacts. Over 70 people were killed, over 100 people were missing, at least at the end of February they were. And many of these deaths and missing people were to do with tunnels, with 2 hydropower dams that were down this valley. And these tunnels were pretty much just blocked with the flood deposits. This event also had a big impact on infrastructure. This is another still from a video showing a bridge. That's a bridge where I've highlighted that is at the moment of being wiped out by the front of this flood surge. The event also completely destroyed one hydropower dam and severely damaged another. You can see in these images, particularly the top photo, that this dam has been completely silted up by rock and debris deposits from this surge. Now, at this point, you might be thinking, this is all interesting, but why are you talking about floods in a talk about landslides? Well, the real question here is, what caused this flood? There was no rainfall on this day, so why did a huge flood surge suddenly hit this valley? Now, initially, the media and some scientists suggested that this event was caused by a galof, a glacial lake outburst flood. Now, a galof it occurs when a body of glacial meltwater, which commonly forms behind retreating glaciers, suddenly gets released. Galofs can be very dangerous and have been observed in the Greater Himalayas. However, in this case, scientists quickly pointed out that we know where most glacial lakes are. They're very well mapped. And actually, we knew that there weren't any glacial lakes upstream of this particular flood event. So this seemed to be a very unlikely explanation. To try and find the cause of this event, geomorphologists began looking through satellite imagery upstream of the flood. Now, this satellite image shows an area just upstream of the dams that were destroyed on the day before the disaster. And this looks fairly uninteresting. This is just some snow-covered mountains, nothing particularly exciting to see. However, if I flick to the same image from the day after the event, you can see that there's clearly been some sort of huge event here. Massive portions of snow and ice across this region have clearly been replaced with dust and debris, and there appears to be some sort of huge landslide event in the northeast of this image. So with this kind of strange thing identified, scientists began looking at it with some more detailed satellite imagery, and it was quickly confirmed that there had been a huge rockfall in this area. Now, these 2 images show the source zone of this rockfall. As with the Langtang event, it appears that this rockfall originated beneath on a slope with a lot of ice and snow. And the arrow here indicates the size of this event, again, over half a kilometre wide, several kilometres long. The image on the right shows the estimated thickness of this event, some 150 metres thick. So a huge volume of rock, again, involved in this collapse. Okay, so we've identified that a rockfall occurred upstream of this flood, but that doesn't really answer the question of how a rockfall caused such a massive surge. Well, this is still an ongoing debate. However, the most likely explanation is that there was a hazard cascade. So you remember from earlier slides, I mentioned that landslides are often hazardous because they cause other hazards. Now, in this case, it seems that the initial rockfall temporarily dammed the Rishiganga River and also caused rapid melting of snow and ice along adjacent hill slopes. This meltwater, combined with that temporary dam being breached, will then have caused a huge surge of water, ice and rock from the rockfall. And as that debris flow kind of traveled down the valley, it would entrain more and more material from the channel, thus causing the hugely destructive flow that caused the impacts I described previously. So, okay, that seems good. We've identified that the rockfall occurred. The rockfall almost certainly caused the flood. So the final question to try and answer is what caused this rockfall? If we want to try and avoid and mitigate similar hazards in the future, it's vital that we fully understand those that have occurred in the past. So we need to try and work out why this rockfall happened. Unfortunately, this is quite a difficult question. Unlike the Langtang event, which was clearly triggered by the earthquake, there is no obvious trigger in this case. There was no rainfall on the day this rockfall occurred or in the days leading up to it. There was no earthquake, no large amounts of seismicity. So was this one of these random stochastic events that I talked about earlier? Possibly, but perhaps a more likely explanation is climate change. Now this figure, this schematic, shows how climate change can influence landslides, and the key process here is permafrost thaw at the top. Now, for those who maybe don't know, permafrost is just ground that is permanently frozen. Now permafrost is actually very stable, and it's been shown to be able to hold rock slopes together. So rock slopes with permafrost are quite unlikely to fail. However, as the climate gets warmer, permafrost begins to thaw and degrade, and rock slopes that were kind of held stable by permafrost are now not held stable by that permafrost. The melting permafrost also adds weight to the slope, so you can go quite quickly from a very stable permafrost slope to a slope that is very likely to fail. Now, it's not yet confirmed that this is the cause of this particular rockfall, but at the moment it does seem to be one of the most likely explanations. Okay, so that's the event. What lessons can we learn from this disaster? Well, again, as with Langtang, a key thing to be able to do is identify these hazards. As I said, glacial lakes and Gloff hazard is well mapped, but these kind of permafrost-related instabilities are not. So we need to have a much better idea of where these events might happen in the future if we are to have a better effort at avoiding or mitigating them. This event also suggests we need better monitoring of these types of hazards once we've identified them. It's now been shown that the ice above this rockfall began cracking in 2017, so 4 years ago. This is a close-up image of one of the satellites I showed earlier from before the event, and in hindsight, we can see, if I show you this red line, a crack has clearly formed right above where this rockfall occurred, 4 years before the event. So this suggests that had we been able to identify slopes like this were at risk and had monitored them, perhaps we could have had some effort or chance of warning people downstream that this was going to happen. And finally, we should just avoid building large infrastructure in these highly at-risk areas. Most of the impacts I talked about earlier were directly due to the hydropower dam being where it was. And the sad thing about this is that in 2013, a similar flood occurred. The Indian government prohibited all new hydropower being built, yet this dam was built anyway. And this really highlights that science, government policy, and local stakeholders need to work together much more closely to try and reduce the vulnerability to these types of hazards. So to conclude, due to their size, mobility, randomness, and potential for cascades, landslides are a major geohazard. This is particularly true in the greater Himalayas, where these examples kind of demonstrate that massive rockfalls associated with earthquakes, glacier collapse, and climate change have had some catastrophic disasters. And this really highlights the need for better identification and monitoring of landslides, particularly upstream of kind of major infrastructure. That's everything I want to say. Thank you for listening. I'll happily take any questions now or later. Thank you.
Thank you very much, Josh. Very informative, beautifully illustrated, just as I expected when you do field work in the Himalayas. We have a few time for some questions. Brilliant. There are some questions here from Janek Codlin. How can scientists today engage communities that are at risk of geohazards, such as those in Nepal, which are reluctant to move or prevent disasters?
I think a key thing is to make sure when we're doing science, we need to do this with local partners. So whenever we go to Nepal, we make sure that we have contacted the University of Kathmandu, that the people there are kind of aware of what we're doing, and they will often help us, work with us. I think if you have local scientists involved, other people are much more likely to trust what's being said if you show engagement. But it is very hard. I think, yeah, you've got to try and get people sat down together. You need scientists, government, local people, all there together. Because often there are issues that we won't even think about. ancient rights of who gets to farm where, some cultural things about, we need to live near this temple. So there's a lot of stuff that we as scientists won't know that we need to consider. So yeah, it's very difficult, but yeah, just making sure we contact and work with local people is probably the key thing.
Yeah, great. Not an easy answer there. I've got another question for you from Amy Brown. How do processes such as weathering play a part in the causation of landslides?
Yeah, they can play a huge part. So one of the major causes of rockfalls is often kind of existing planes of weakness in rocks. So various discontinuities caused by faults or fracturing. And these faults and fractures can easily be exploited by weathering, such as freeze-thaw. So in these high Himalayan mountains, if you've got permafrost that is kind of degrading, freezing, that can easily severely weaken the strength of the bedrock, making landslides much more likely.
Great, thank you. This is a question from Neve Bluff. I hope I got that right. Question for you about you, Josh. How did you get into this specific area? So what's your motivation for studying landslides?
Yeah, good question. So I actually, by pure luck, I happened to be in Nepal just after the earthquake in 2015. So I kind of saw the impacts of that earthquake and the landslides and stuff. And I'd always been interested in geology. So that very much drove my decision to swap from geophysics, which I'd done as my undergraduate, to this hazard stuff. So yeah, for me, it was kind of seeing on the ground these impacts that caused me to make a decision.
A very personal sort of experience then. It's quite unusual in many ways.
Yeah.
Great. We have one other question, but that's for Zoe, but she's just disappeared off my screen. She may reappear, so we'll come back to that one. That's could British buildings survive a big earthquake from Paul Hart? Interesting questions, because we do get earthquakes, of course, in the UK, but they tend not to be big. So we'll reserve that question for Zoe later on. She's probably just popped out to make a cup of tea. It's just a few minutes past 11, so we'll move on to our next presentation, which is from my colleague Dr. Alan Smith, who I can see, which I'm very pleased about, sitting in the screen there. So Alan's going to be talking about flooding in a warming world for the next 20-25 minutes or so. Okay, Alan, great, over to you.
Excellent, thanks, Greg. I'll just share my screen. I haven't disappeared for a coffee break like today, so hopefully I will give us some time to return. As Greg said, I'm going to just put over the next 20 or so minutes, try and give a really whistle-stop tour into flooding and think about how that may be impacted by climate change. As Greg mentioned, my name's Alan. My role in the School of Geography, Earth and Environmental Sciences is as a lecturer in environmental management. I'm also the admissions tutor for geography. But flooding, in particular, how floods are caused, how they propagate throughout the environment, as well as how they impact on humans, is a large part of the research that I do. So really spanning the social and the natural sciences and the subjects we cover here at Plymouth. So in today's short session with you, and thanks for tuning in and bearing with this succession of presentations, and whether this is for personal interest or you're thinking of your next steps, regardless of subject area, then hopefully you're finding some interesting new case study material, just new updates from all of these different presentations. But I wanted to talk to you today about the context of flooding as a natural hazard, and kind of global context of the impact of floods. I'm going to touch briefly on climate change and what we can expect, and how we can expect within a change of climate, how we can expect the regime of flooding to change as well. Some of these could all be a conference or a talk in their own right, but I'm going to try my best in 20 minutes. And then I'm going to I've cut down to just talk about the three most common types of flooding in the UK, and pluvial, fluvial and coastal. I'll talk a bit more about all of those. And I wanted to end on an Australian example. And if you've been following the BBC News or other news websites, you'll see that this has been in the news this morning and this week, with some very severe flooding happening on the eastern side of Australia at the moment. Of course, they're going into their autumn and winter as we're about to go into our summer. This infographic shows a distribution of by percentage of all weather-related hazards or disasters, I should say here. So these are hazards, so natural processes that are then impacted on humans and become a disaster. And of all of those weather-related disasters, 56% of those globally between 1995 and 2015 were flood-related. And you can see some of the other most common types there, from droughts, 26%, extreme wind, 16%, not quite registering on a percentage point, but you can see wildfire as that small orange circle there. Again, that's something that's been in our media over the last year or two in the UK, and also more severely in places like California and Australia. But I'm going to talk about floods today, and we can see here that globally in this time period, or number of people affected or flooding was 2.3 billion people in that time period. So a substantial amount of the Earth's population, more than a third, or around a third, depending on how you map the population at this time period. So it has a major impact on how we all live our lives, and I'm sure some of you are aware, some of you may have experienced flooding yourselves, either in different countries or particularly here in the UK, or you may quite commonly may know someone who has, or have seen the aftermath of flood damage. So bringing things a bit closer to where we are currently, other than on Zoom, but in England and Wales, this map on the right-hand side shows the potential extent of flood risk in England and Wales. And you can see, as you may expect, particular flood risk, you might be able to identify locations where you're currently based on significant areas of flooding, particularly around coasts and major river estuaries. So I guess you don't have to be too much of a geography pub quiz expert to hopefully try and guesstimate some of your English and Welsh River Geography Network trivia going on there. This is a really interesting report. It's a few years old. It's a little bit older now, but I think it's, in terms of hindsight, which is talked about a lot now, I think really fascinating. But government report, so the UK government's National Security Strategy in 2010 outlined the greatest risks affecting the UK. I might get this number wrong off the top of my head now, but we've got, and this report, so the time here is important, but 2010, the greatest threats to the UK. So natural hazards was not one of those, and particularly flood risk, and interestingly volcanic hazard, and Paul may talk more about this later on, but particularly on the economic impact of volcanic hazards in the UK following that global kind of air travel shutdown and the volcanic Icelandic ash crisis, something that we're probably a bit more common experiencing now in terms of travel shutdown for a very different reason at the moment. But flood risks in the UK in terms of their economic damage as well as the fatalities that they cause. Other major risks that are grouped in this category as threats to the UK's national security were the things that we might expect, so international terrorism and cybercrime. But particularly hazards get a very special and high level mention there, and obviously not necessarily for desirable reasons for any of those categories. And just as a bit of context, in England, 5.2 million properties are at risk. That's a very vague term. Lots of hazard and risk mapping considers properties, but their properties can be very variable, from whether it's a university campus or a school building to a residential house, residential or leisure building, and so on. And roughly 5 million people live and work within flood risk zones, live or work within flood risk zones. Some of my research, which I'm not going to cover today, but looks at how populations move through space at different times of the day. We've just had a census. Last weekend was Census Day, so you would have filled out a census form, or somebody may have done that on your behalf. And we're not always, we're not just at the location where we say where we stay overnight on Census Day last Sunday. We all travel for leisure and for work to all sorts of different locations, and our exposure to risk, whether it's flood risk or even the hazards we've already looked at on these presentations so far, drastically changes depending on where in the world you are, of course, as well. So how can we relate this to climate change? And this could be a hotly debated topic, but it's now with very high confidence and accepted by scientists and researchers around the world that climate change is caused by anthropogenic CO2 emissions, amongst other things, so human-based factors. But regardless of how and who causes those, something that we are certain by is what that means for how it's going to change the world that we live in, regardless of those causes. And this is, we can look at the Intergovernmental Panel on Climate Change's fifth assessment report, so a major influential report on climate change, and these are updated periodically as an international collaborative document and research publication. And I've just highlighted a lot of text on these slides, so apologies, but I just highlighted some key points here. That sea level rise and increase in extreme rainfall are projected to further increase coastal and river flood risk in Europe. And importantly, without adaptive measures will substantially increase flood damages, so affecting people and also financial and economic losses. And that's predicted with a very high confidence. I'll make a look at some other research that's been conducted. This is in the journal Nature Climate Science. And I've just very briefly summarised some of these findings here. But what we can expect for the UK, so we can see what's mentioned for Europe there in a global context. But in the UK, we can see that possibly there might be some predictions suggest there might be a decrease in the amount of rainfall we get in the UK, but really significantly, there'll be an increase of the number of high intensity days. So the rainfall that we do get, even if it stays the same or goes down very slightly, will occur in much shorter durations, higher intensity bursts of rainfall. And that has some really important and quite devastating impacts on how we manage flood risks. So a lot of rainfall falling on small areas all at the same time. And we're going to show you some examples of this in today's session. Really limits natural and urban systems for managing that flood water, and then the consequences that can help that hazard develop into a disaster. Complicated squiggly line graph, but don't switch off at this point. What I just want to show you here is to focus on the black dashed line. And you can see over the last 120-ish plus years or so, that average rainfall in the UK has been increasing. And there's lots of reasons for that, but one of those is that with a warmer atmosphere, atmosphere can hold, in our particular maritime climate where we're positioned, or the island that we happen to live on is positioned, more moisture can be held in the atmosphere. And in turn, that can generate higher rainfall and more variable rainfall. There's lots of other lines on this graph, so historic maximums and minimums in terms of rainfall. But I just wanted to point out that actually this is a measured record, and this shows us that this trend that rainfall, the amount of rainfall we've experienced has been increasing, even if future predictions suggest that it may not increase further, but actually might just become more intense. So we can't quite see what's going to happen yet on the right hand side of this graph. And to use some creative imagination of what we may think could happen under different climate projections. I'm really pleased that Josh mentioned some of this earlier, because I intentionally was going to have a disclaimer here saying that I wasn't going to talk about some of these different causes of flooding, particularly around tectonic causes and floods that can be a secondary hazard following an earthquake or a landslide and so on. But this overview diagram shows the key causes or the principal causes of flood risk in terms of the physical causes. And we can broadly break these down into river and coastal floods. And I'm going to talk about flooding from excess rainfall as a separate category later on. And if we look at the river floods branch of this diagram, we can see that can be subsequently broken down into three subcategories. So the atmospheric hazards. So again, rainfall entering those water systems and those drainage channel networks. Snow melt, something that we don't get lots of in the UK, but it has been linked, particularly in the 1940s, to very severe flooding in the UK. In fact, some of the worst flooding the UK has experienced what happened in 1947 as a result of large-scale snow melt. And ice jams, again, something that Josh has mentioned already and not something we experience in our climate in the UK. We've mentioned tectonic hazards and landslides already, and touched upon technological hazards, so dam failures, whether that's as a consequence of a natural process, or whether it's through a construction or engineering failure, or some sort of human impact or aspects there. And then if we look at the final branch, we can look at coastal flooding, again, atmospheric hazards, and I'm going to talk a little bit about storm surges, and then tectonic hazards in terms of tsunamis, which I've taken out of today's presentation. I guess we're familiar with the large and devastating tsunamis, especially linked to some of Zoe's research we've heard about already from Japanese earthquakes and the Sendai earthquake in 2011, and probably quite famously, if you've watched a film on Netflix, I always forget the name of this now, I think it's the one with Nicole Kidman in, but the Boxing Day 2004 Sumatra hazard. Somebody could have always need reminding of this film name in the chat if somebody got it off the top of their head.
Impossible.
Ah, excellent, thank you. Impossible. Yeah, quite a tricky one to watch actually, and sad, but really interesting in some of the hazards associated with those flood hazards and what's actually in the water, and how humans are incredibly vulnerable. So just want to give a brief introduction here into to the three particular types of flooding I wanted to just highlight because they're some of the most common in the UK. One of those we call pluvial or surface water flooding, and essentially that occurs when the rainfall that's hitting the ground cannot drain away quickly enough. Quite common in urban areas where large areas are extensively sealed by road networks, by tarmac or other impermeable surfaces, or by buildings. And can also occur in non-urban environments as well, so particularly if the ground's frozen or if it's baked very hard dry. Not as common in the UK, but does occur here, but but can be a principal hazard in other parts of the world as well. This photograph just shows the main road in Southampton, which some of you, if you've been or lived there, may be familiar with. This is the road going in front of IKEA and the Southampton docks. But again, that short-term disruption, incredibly expensive duration if you write your car off driving through some of this flood water. So probably less likely to result in a fatality, but cars trapped in floodwater like this do result in fatalities in the UK. And again, significant disruption to everyday services as well as emergency responses. I've alluded to, in the final bullet point here, I've alluded to urban sealing, and I want to use London as an example. And this might be something that you may be aware of yourselves already, or I'm sure you can definitely think of your own examples of urban sealing from the places you live or visit as well. But London's quite an extreme example, but this photograph illustrates it well. So you can see here what would have been a more permeable surface or a traditional front garden for a terraced house on this street in London has been paved over. It's very nice. I'm cautious to talk about this with geologists in the virtual room. Some sort of slate tiles, I presume, by the looks of things here, but not very good for channeling rainwater through into the ground, and this kind of human modification of the landscape. There's been an increased trend over the last 20 years in London, particularly increased car ownership, increased population, and cars having some households having multiple occupancy or multiple cars per household. So a huge demand for increased off-street parking. As I guess if anybody that visits or lives in a major city probably has this to contend with on a regular basis. It's actually estimated now that in London, 2/3 of gardens are completely sealed or at least partially sealed. They're quite a small impact on an individual level, but if you aggregate those together, so combine that total area, then that's equivalent to 2.5 times the area of Hyde Park. So a major area of surface sealing. Again, that water has to go somewhere. So typically, and especially in the case of London, it ends up in urban drainage systems. So we can think of very quick runoff, very quick peaks on a hydrograph or a discharge, and again, that contributes to speeding up the flow of networks through an urban area. But when there's too much water, that causes flooding and problems for managing that risk. The Royal Horticultural Society did their own survey. They estimate around half of front gardens have been paved over in London. So difficult thing to quantify, could be an interesting project or independent type project. It's something I want to look into a bit further, looking at the satellite imagery and different map-based data and the kinds of things that I'm looking at. We're probably all very well, probably all know river flooding, or what we call fluvial flooding, very well. This is an example from the 2013-14 floods on the Somerset level. So again, this might be a location where some of you are from or very familiar with. There was a really big debate, political debate around these, not just the physical and natural processes, but how they were managed. There was a lot of debate about dredging the rivers to stop the flooding. So there's lots of connotations there on how flooding should be managed. But even with this high volume of water, even if these rivers were dredged, it would not be possible to fit that volume of water within those channels, even if they had been dredged. Of course, there's a strong argument for doing this, and there's lots of very valid reasons how dredging can help, as well as some negative impacts. But humans can have a large impact on flooding, and it depends on a large scale of factors. How catchments are managed, so by humans, whether we're paving over parts of catchments, whether we're deforesting upper slopes of catchments. River flooding can also be driven by the physical catchment characteristics, so the shape of the catchment, for example, the steepness of the catchment, and also what we call the antecedent conditions. So the preceding levels of rainfall if the ground's already saturated, meaning that more water will run off into river channels and networks and so on. Coastal flood risk is something that we're all very familiar with, and globally, and again, particularly here. So some of us fortunate to live on the coast in Devon or Cornwall or elsewhere, this might be something that you're very familiar with, especially if you've got the train between Plymouth and Exeter, whether it's for work or education or for leisure or holiday and so on. You've probably seen, or you've certainly seen, the news stories of the sea wall and the impact, and I'm going to highlight that on the next slide. But coastal flooding can occur, so increased wave height, so due to wind, so the impact of wind kind of building up higher swells that can overtop existing defences or flood lowland areas. And in a much longer term, climate change can have an increase in that sea level rise through the melting of ice, water stored as ice on land, contributing to sea level rise, but also the thermal expansions of the oceans. As they're heated, that water expands and occupies a greater space, resulting in a sea level rise. But also can be caused by temporary increases in sea level height, can also be caused by atmospheric pressure. And that's what we think about when we talk about a storm surge. This equation, which I'm not going to go into in lots of detail here, but we can define a storm surge by looking at the pressure deficit, so by measuring atmospheric pressure or the change, and as a function of this, what's the Greek letter rho, so the density of water and its acceleration due to gravity. Those two combined we call the specific weight, so the specific weight of water and a change in atmospheric pressure. And a much easier way of thinking about this, especially if you're tuning into the weather forecast, or the Met Office app tells you the pressure forecast as well. 1 millibar in pressure decrease equals a rise in sea level by 1 centimetre. Of course, this is only temporary, but those can all build up, especially in low-lying areas, and also areas where coastal defences are particularly vulnerable. Just some photographs here, not my own photographs, but I've taken these off of the internet of your minimum 2014, made national headlines, but 100-metre stretch of the Dawlish sea wall was destroyed by a storm surge in the winter flooding in Dawlish, so South Devon at that time. Major impact, it took 2 months and cost £35 million to repair this wall, so essentially cut off the only railway connection into Devon, the rest of Devon and Cornwall. So a major local and regional issue there. And it's estimated that this being closed cost the local economy over £1.2 billion. So in impacts on business and in work and so on. So again, some very difficult human things to consider there. I probably should have reworded this title, but the impact, this probably what I wanted to kind of just briefly talk about here was the impacts of flooding on humans. So we've talked about some of the physical processes of flooding. I'm interested in how humans are exposed to flood risk and where people are and when they move around. So not just think about where people are at night time, as I've mentioned, but where people are at different times of the day. But if you've ever been flooded or know somebody that's been flooded, or maybe you've known this from previous examples or case studies, flooding can have quite a severe impact on humans. I guess that's a major understatement. But particularly if you're a household, so contamination of your carpets and your plaster. So water isn't that nice kind of tropical Caribbean water if you're at the beach, or the nice tropical water next to Dawlish on a sunny day in Devon. But it's mixed up with all sorts of horrible things, seawater, which isn't good when contaminates freshwater or buildings, sewage, raw sewage, oil and other pollutants and chemicals. So essentially not things you want to have in your house. Once soaked into furniture and plaster, those things need to be disposed of. There's not really much that can be done at that point. There are some now designs for more flood resilient houses and homes that might have particular designs inside, so tiled floors, particular paintwork on wall, and where electricity sockets are placed to help with that clear up process. There's some health impacts, so suffering from mold, obviously from fatalities, is probably beyond a health impact. And in other parts of the world, dysentery and spread of waterborne diseases as well. Displacement of people, as well as the economic impacts, whether that's on a major large scale or on small local scales. And also on an individual level, isolation and cut off from loved ones, being displaced from your household and so on, or other friends and family or social support networks. Just cautious of time, I wanted to wrap up on an example focusing on Australia. And you may have heard of or covered El Nino before, and we can see this infographic or this diagram shows in an El Nino year, or you may refer to this as ENSO, the El Nino Southern Oscillation, that you can see this equatorial thermocline, so suppressed upwelling of colder currents off the coast of Ecuador. And that has a global or has very far-reaching impact. So you can see the impact further to the west on towards Australia is cooler than normal temperatures and actually reduced chance of rain. This is a periodic, naturally occurring process, but actually has been strengthened due to human influences on climate change. The opposite, we can think about the opposite is true, or a La Nina year. So we actually get cooler than normal or stronger upwelling, so colder currents coming to the surface off the coast of Ecuador. That's combined with very strong trade winds, westerly winds across the Pacific or this equatorial region. And actually, as a result for Australia, that increases and warmer than usual. So increased convection and evapotranspiration, warmer air can hold more water, more moisture, and there's actually an increased chance of rain, particularly in Australia. I've mentioned this in there today because that's what's occurring in Australia today. And as we're speaking now, major rainfall and flooding is affecting people live and in real time in Australia. This isn't a map from the Australian government, but this shows an average, the change. So the bluer colours on this map are wetter, more rainfall, so mean rainfall increasing or likely to be exceeded, and this is what happens in a La Nina year. So linked to that diagram I've just shown, where we can expect, or where Australians can expect, higher rainfall. I just want to sum up on final slides here as a quick case study. This wasn't this from this year, but 2019. So the town of Townsville, Queensland, Eastern Australia, quite a large city, so 230,000 people. Unprecedented rainfall, over 1 metre of rain fell in a month, and also in one point a year's worth of rain in 1 week. Ironically, the dam built to prevent running became overfilled. It reached 2.5 times its capacity, and that became dangerous and liable to collapse. You can see here this graph, so the orange line on this graph just shows the monitoring of the dam, the reservoir level behind the dam, and that went up to in the end over 250% capacity, so at risk of a major technological hazard and dam breach. This is what the Ross River Dam should look like under normal circumstances, and this is what happened in 2019. So emergency planners had to make the difficult decision to release rapidly large volumes of water to stop this dam suddenly failing. As a consequence, that caused major flooding in Townsville. These are some of the highlights, or I shouldn't say highlights, some of the news stories that came up from, of course, people's livelihoods and homes and life savings being devastated, but also has other secondary effects you may not appreciate it. So crocodile warnings as different kinds of wildlife interact with humans in urban areas. This was Townsville Airport. So again, completely temporarily closed. No way it's possible to land aircraft here, whether it's for evacuation purposes or to fly in support and relief. So the human management aspect there is very tricky and difficult. And it wasn't just humans that this flooding affected. And I want to kind of summarize here by just providing on this final slide kind of closing the loop almost. This is the barrier reef off of the east coast of Australia. This is the discoloration of the flood water from Townsville. This water, this photograph is actually taken 37 miles off of the coast of Australia. So that flood water extended a long way out to sea. Incredible impact on silting up delicate coral systems, and there's very biological biodiversity hazard there on a reef that's already very fragile. I just wanted to end on a quote from David Attenborough from the Blue Planet television series, that the future of all humanity, indeed all life on Earth, depends on us. And I think this photograph for me really sums that up. The CO2 emissions that we might emit by living in the UK, by our lifestyle practices, by what we do, what we buy, maybe even what we eat, is not only affecting global climatic systems as far away as Australia, but those in turn are also affecting the aquatic environment, and as far as this extreme example shows, 37 miles offshore. So I'll summarise there. There's a whistle-stop tour of some of the major types of flooding we experience in the UK, but also some of the global impacts of humans on the global climate and flooding. More information's we've got a YouTube channel for the university, and there's a School of Geography, Earth and Environmental Science playlist there, and I've seen there's some talks from Zoe and our next speaker Paul on there if you want to catch up with any of the things we're doing at Plymouth and use those, and you can also find us on our social media pages. I'm cautious of the time, so I'll stop sharing my screen and stop talking there, and if there are time for questions I can answer any, but otherwise I can monitor the chat as well.
Thank you very much, Alan. Brilliant talk. Lots of food for thought there. Great. And there is some questions already. So we'll do a couple of quick questions and then move on to volcanoes. So thinking about flooding, there's a question from Laura Taylor. Seeing there are so many risks towards humans as a result of flooding, why do the government continue to build housing and other developments on floodplains?
Yeah, I would like to know the answer to that as well. Really tricky. I think anybody that lives next to a major development and there are planning processes where flood risk assessments are required, it seems to me completely bizarre how some of those are ignored or passed through kind of vague levels of mitigations. Certainly new developments in floodplain areas don't help. They increase that physical exposure, so it creates that potential for a disaster. But also, like the London example, which is an extreme one, but it increases the amount of area that's surfaced and impermeable to flood, to rainwater, particularly in more urban settings. I don't know, I'm afraid. I can't really give a concise answer to the crazy system that's sometimes used by government and policy decisions. Yeah. So
are some of those decisions made locally, though, regional governments, as opposed to a national decision, or is there a guidelines that are national level?
Yes, I think there's a mixture here. So certainly through things like the Town and Country Planning Act, there's certainly local provisions put in place, and lots of those policy or planning decisions are often initially in the first instance made at the local authority level, but then it can be escalated up to government level for appeal and so on. So certainly national policy is driven on funding to retrofit houses in areas that are at risk, or provide additional funding for flood defences, which is also politically hazardous in, say, where that money in the UK goes, particularly north-south divide questions. There's a huge debate wraps up around all of those things.
Okay then, well, if there's not any further questions, and there doesn't seem to be any more coming through the chat, thanks Alan, thank you very much. And we'll move on to our final talk of this Geohazards conference, and that is from my colleague Dr. Paul Cole, who will be talking about volcanoes and the real death in paradise. So over to you, Paul.
Thanks very much, Greg. So it's nice to have the final slot, obviously, in this talk, and I'm going to be talking about volcano stories, and as Greg says, the real death in paradise. I'm actually going to be talking about the island where they actually filmed Death in Paradise, which is Guadeloupe as well. So for those people that are fans of the program. So Zoe has shown you this map previously, just to kind of set the scene from a kind of plate tectonic point of view. We're which shows the plate boundaries. And I'm gonna focus in on the Eastern Caribbean, sometimes known as the Lesser Antilles, but better perhaps known as the Eastern Caribbean these days. And in that area, we have basically an arc of volcanoes, or an arc of islands, and the Atlantic plate, which is it's a subduction zone. So the Atlantic plate is being subducted underneath the Caribbean plates, and one can really believe in plate tectonics in this region of the world. We've got a trench here, and obviously volcanoes and the resulting magmatic activity, which is generated by this subduction. So this map shows the volcanoes of the Eastern Caribbean, and they range from Ceiba in the north to Grenada in the south. There are 20 live volcanoes here. We are going to visit 4 of them in this brief talk in the next 20 minutes. We're going to visit, I'm going to do those in terms of time. We're going to start with the oldest eruption or volcanic crisis first. We're going to start with Martinique and Montserrat here. I'm going to move to Guadeloupe and talk about a crisis in the 1970s. And we're going to move to Montserrat with the eruption which started in 1995. There's been no eruption there since 2010. But of course, many of these other volcanoes could have erupted as well. And then finally, I'll finish up talking about St Vincent, where a new eruption started at the end of last year and is currently ongoing. So actually the only ongoing eruption. I'm going to also talk a little bit at the end about risk, volcanic risk, and how that differs from hazard. There are something like 3 million people that live on these islands. So there is a considerable risk that is not evenly distributed, and I'll finish up by talking about that. But I'm largely going to be talking about the hazards, about the actual volcanic eruptions and what the hazards actually are. So first of all, we're going to go to the island of Martinique. But just before I do that, I just want to talk a little bit about these islands. We talked about the actual active volcanoes. But in actual fact, these islands have been volcanically active for millions of years. And this plot here shows the different islands, some of which I'm going to be talking about, but the vertical lines here show the duration of some of the activity. And the areas in red at the top here are just the potentially active volcanoes. So you can see that there have been volcanoes active, and those are not necessarily the same volcanoes. I've moved the lines across there to show the different volcanoes that have been active through time since the Miocene, across at least the last 14 million years and possibly longer. So the first island I'm going to talk about is Martinique, and you can see that there have been at least 4 different volcanic periods separated by a couple of million years, a time gap before the current active volcano. So let's go to Martinique, the island of Martinique, French island of Martinique here, which are meant to have the shape of a mitten. Let's see, there's a thumb here. But the key thing that you can see in the volcano we're going to focus on is Montserrat here, which is the currently active volcano. And you'll see that there's it's all volcanic. And what's happened is if we look geologically, the older volcanic edifices to the south here, and then this area, what's known as Mont Jacob, is actually a couple of million years old. So volcanic activity has shifted through geological time towards the north. So we're going to focus on Montserrat. And here's the island of Montserrat, and the volcano of Montserrat, and the town of Saint-Pierre, as it looked about 10, 15 years ago when I took this photograph. So Saint-Pierre, the town, was known as, back in Victorian times, known as the Paris of the West Indies. You can see here the harbour absolutely packed with ships. It was a bustling town, really very pleasant place to live. And unfortunately, of course, this was an active volcano, and then in 1902 it came back to life, and there was an eruption. I'll just show you the impact of that eruption. You can see there, if you just go back, you can see the town here, and the town was completely destroyed by what the phenomena that was known as pyroclastic flows. You've probably heard about pyroclastic flows. These are fragmental flows of blocks, ash. They're incredibly hot. They can be at temperatures up to 600 or 700 degrees centigrade, and they can move at high velocities. And we know from studying the effects here, you can see that the buildings have been pretty much razed to the ground. There are a few walls standing, but you can see that huge, great rubble, masonry, buildings completely destroyed. And we can see there, if we look at the map that we've got here, that that area that's been destroyed is an area, a sector, just to the southwest of the volcano. And we know this is a type of pyroclastic flow known as a directed blast or a lateral blast. And that means that it had relatively high velocity, so velocities in excess of 100 meters per second, so really very high velocity, which means it had a high destructive potential. So this was a major disaster. 30,000 people were killed in the town of Saint-Pierre. There's a huge story, which I don't have the time to go into, about the politics of why those people were not evacuated. But it's a major volcanic disaster, one of the major volcanic disasters of the 20th century. Now we're going to move islands now, another French island, to the island of Guadeloupe, which, as you can see, is a butterfly-shaped island here. And the island, interestingly, the part which has the volcano on it is known as basse terre, which means low ground, which is slightly strange. But the volcano is down here. It's opposite of Martinique. What's happened here is that with geological time, the volcanic center has moved southwards. So the active volcano is down here. Now, in terms of the hazard and risk, this photograph here shows you the town of basse terre, which is just down here on the western side of the volcano. And here you can see the top of the volcano in the distance. And there are something like 70,000 people, certainly in the 1970s, there were 70,000 people that live in this town. It's a major town on the island. It used to be the former capital. And what happened was a volcanic crisis developed where the volcano basically came to life. Here's a photograph of some of the activity. You can see there was actual manifestation of activity with small explosions occurring. And you can see that there was clearly tephra on top of some buildings that were close to the volcano. So there was an ashfall hazard. And as a consequence, 70,000 people were evacuated from the town of basse terre. However, this didn't develop into a full-blown eruption. What do I mean by that? What I mean is that the activity was phreatic. There was no new magma involved. Yes, there was actual small explosions being occurred, but no magma reached the surface. It was just hot rock meeting groundwater, which caused these explosions. Yes, there was still a hazard. The hazard was ashfall, but it did not develop into a full eruption with pyroclastic flows like happened in Montpellier, Martinique in 1902. So those people, the 70,000 people that were evacuated, were eventually allowed back to their city. And there's a great controversy about whether those people should have been evacuated anyway. So that's the crisis of Guadeloupe. So I'm going to move on to the island of Montserrat now, which I'm sure many of you are aware of, the eruption there, which started in 1995. This map is actually a satellite image, false color satellite image of the island of Montserrat, and it shows very nicely the location of Soufriere Hills volcano that you can see there, and the products shown as a pale white and grey colors, which are largely the products of pyroclastic flows which have been formed by the eruption. So in terms of the island itself and the people that lived there prior to the eruption, there was a population of 11,000, and now it's around about 5,000 people that lived there. The capital, interestingly called Plymouth, which is just here on the western side, was pretty much completely destroyed, and people had to move to the northern part of the island. So many of the problems in terms of managing this long-term eruption started in 1995. The last magma extruded was in 2010. was a result of this lack of space. And at the present time, people are living in this region here, which is in the northwestern part of the island. So they're effectively now living in an area which is 6 kilometers long by about 2 kilometers wide. And that's partly because of the small nature of the island, and also the fact that the topography is very rugged. So it's the center hills here rise to something like 700 meters. The other thing about Montserrat that's worth thinking about is that Montserrat, of course, is a overseas territory of the UK. So the British government is ultimately responsible for the people, and the economy there is funded by 50% of the economy is from aid funds from the UK taxpayer. So in terms of islands in the Caribbean, Montserrat has a relatively unique status, perhaps more like the French islands, and being a kind of responsible for the British government. The French islands, obviously, the responsibility of the French government. But many of the other islands that are independent wouldn't have had the money to monitor the volcanoes. So what actually happened at Montserrat? There's often some myths about what went on at Montserrat. The key thing that happened is the eruption in 1995 until 2010 involved the extrusion of a lava dome. Now, lava domes are very different from the kind of basaltic magma that you see at Mount Etna, currently erupting literally almost as we speak at Mount Etna, and also the eruption which is ongoing in Iceland. That magma and lava is basaltic and has a much lower silica content, probably around about 50%, 49% silica, and that means it's far less viscous, or far more runny. In fact, actual fact, the magma that was erupted at Montserrat was probably about 1 million times more viscous than basaltic magma. And the problem with that is that when it reaches the surface, it simply cannot flow. And so it piles up over the vent and it looks like a jumble of rocks. And here you can see this lava dome. The lava dome was extruded in Montserrat. This picture I took in 1997. It's about 1 kilometer across. It cannot flow, so it just gets steeper and steeper. You see it at night time, it glows, and what you can see here are not lava flows at all. What they are incandescent rock falls. Incandescence in rocks only happens at temperatures of above about 550 degrees centigrade. And we know that this magma, this andesite magma, when it reaches the surface, had a temperature of about 850 degrees. So these are crumbling parts of the lava dome which are falling off the sides of it. And that's the problem with lava domes, is that they just get bigger and bigger and become more and more unstable until they start to collapse. So what we can see here, this is the major hazard, which is a pyroclastic flow, similar but a different mechanism to the pyroclastic flow which happened at Martinique. This one is simply formed by gravitational collapse, almost like a large landslide of the lava dome, the growing lava dome. It produces ash because that lava dome is stressed and contains gas. So when it fragments, and the ash fragments, it produces these billowing ash clouds. The temperature, we know because we measured the deposits just afterwards, is something like 650 degrees centigrade. So it's cooled a little bit from the 850 degrees centigrade at the top of the volcano. And sadly, this pyroclastic flow resulted in the death of 19 people. This was on the 25th of June, 1997. So these pyroclastic flows result from the collapse of lava domes. Now, just to illustrate this a little bit better, I've got the phenomena of pyroclastic density currents or pyroclastic flows. We can also see these from looking at thermal cameras. And one of the ways that volcanologists monitor volcanoes these days is using thermal cameras. If you've looked at any of the footage or the monitoring from Mount Etna, they use thermal cameras there. So what this is a relatively low resolution, and it's sped up. It's not in real time, but it's a video of an explosion, a volcanic explosion which occurred at Montserrat in 2010. And it shows you very nicely some of the you can see the materials thrown upwards, and then we can see a pyroclastic flow extending down towards Plymouth and a small one in this direction. Let's watch it again. You can see the hot lava dome at the top and then an explosion occurring, tephra being thrown upwards and it collapsing back downwards. So what's happening here is we effectively have a collapsing fountain. So this again is a different mechanism for generating pyroclastic flows. This is an actual photograph of the same event. So here we can see largely being obscured by the ash. You can see the ash billowing off the pyroclastic density current or pyroclastic flow, which is extending in this direction down to the west, one extending to the north here, and you can see there's another one down to the east. So we're seeing pyroclastic flows extending in many different directions, effectively extending radially, as well as the billowing ash cloud above it. So what I want to sort of highlight really is so far we've seen a number of different mechanisms. We've seen pyroclastic flows generated at Martinique, which was a lateral blast. We've seen pyroclastic flows generated by lava dome collapse, and we've seen pyroclastic flows formed by what we call fountain collapse, Montserrat, and in a moment I'll be talking about that at another island. So here's the process of fountain collapse, where we've got material tephra being ejected upwards and then collapsing back downwards and forming pyroclastic flows in different directions. Here we've got a lava dome. This little cartoon demonstrates the process of a lava dome collapse. These steep, viscous lava domes, and they become unstable, and those just crumble generally in one direction at a time and form these relatively slow-moving pyroclastic density. You still can't outrun them. And then finally, the mechanism that we saw at Montpellier, Martinique, which was a lateral blast, where we have effectively a sideways explosion. And the difference between lava dome collapse and lateral blast is that the pyroclastic flows that we see being generated for lateral blasts are much, much faster, and then consequently much more destructive. Now, I'm going to move the final island I want to talk about, and eruption I want to talk about, is Soufriere St Vincent. Unfortunately, the box has just moved slightly. St Vincent is just here, so towards the southern part of the island arc. And St Vincent is actually the most active terrestrial volcano in the Eastern Caribbean. You might think that Montserrat's the most active one. It's not in terms of actual eruptions. St Vincent is the most active volcano. It's had, as you can see, there are 4 explosive eruptions in historical time. That's since 1700. Historical time in the Eastern Caribbean is 1700, when just after colonization by Europeans. And we know from geological studies there's been other explosive eruptions, so 6 explosive eruptions in the last 900 years. If you're wondering which the most active volcano in the Eastern Caribbean, is actually a submarine volcano, which is called Kikum-Jenny, which is down here just north of Grenada. So this is an image of the crater of St Vincent, and here we can see the lava dome. This is what it looked like up until 27th of December 2020. This is the lava dome that was formed by the last eruption, the end of the last eruption in 1979. So I'm just going to go to 1902 again. You remember 1902 was a significant year, because it was the year that the volcano in Montpellier in Martinique erupted and killed 30,000 people. Well, interestingly, the day before that eruption, on the 7th of May, St Vincent also erupted and produced a devastating eruption. The map that you can see here is the map which was shows the area impacted by the pyroclastic flow, which was formed probably by eruption column collapse or fountain collapse, the same mechanism that produced the explosions in Montserrat, and it killed 1,500 people. The fact that 30,000 people were killed in Martinique the following day kind of largely overshadowed what in itself is a major volcanic disaster. Here's some of the effects of these pyroclastic flows on the flanks of the volcano. You can see these huge trees, there's a person here for scale, which have been felled by these pyroclastic flows. So this was a significant eruption. Now, since 1979, the volcano had been quiet until the 27th of December. And then a new eruption has just started. So here's the lava dome. I showed you a picture of the crater, the lava dome, which has got a little bit of vegetation, which has grown in the last 41 years. But then out popped this lava dome pretty much by surprise. There's very little precursory seismicity associated with this lava dome. And this little small dome appeared. And this photograph was taken 2 days after it started erupting on the 29th of December. Interestingly, somebody pointed out on social media that it looks somewhat like a Tunnock's tea cake. Now that lava dome has continued to grow, and what this time lapse here, this is a slightly unusual, perhaps might be unfamiliar to you, but this is much of the monitoring that we do on volcanoes is done from satellites. And what I've strung together here is a time lapse of radar images. And what you can see is the crater. This is the crater of St Vincent. And you can see the lava, the 1979 lava dome just here. And so if you watch here, you can see the new lava dome growing and getting bigger. It's now an elongate structure in this area just here. Now, as well as the potential hazards at the moment are very low in St Vincent, and probably one of the major, because the lava dome is contained within the crater, the major hazard really at the moment is from volcanic gases. And you can see the vegetation damage which has been produced by the volcanic gases from the emission of this lava. You can see here's the unaffected vegetation in green, but you can see the dead vegetation in brown in this region across this side of the volcano. And this is being caused by hydrochloric acid, which is being emitted by the lava itself. So the downwind zone of the dome is generating this, destroying the vegetation. Now, in terms of the dome growth, one of the things that volcanologists like to do is to constrain how quickly magma is reaching the surface. And they do that somehow by mapping the dome. And that's been done using satellite imagery, as I've just shown you, the radar imagery, but also using a drone, from flying a drone in this area and generating digital topography of this region here. And you can see these different times showing the footprints of the dome and how the dome has grown since the end of December up until just a few days ago, 4 or 5 days ago, was the last outline here. So you can see what's happening is this lava dome is actually filling the moat, which this is the 1979 lava dome here, and the edge of the crater rim. So what it's producing is this moat filling kind of thing. And this is just a little photograph to show you some of the detail of the surface of the lava dome. Rather interesting features about giving us information about the way that this eruption the lava is being extruded. The question, of course, is whether this eruption will become an explosive eruption. Will it stay effusive, just forming this nice lava dome, or will it have explosions, which are obviously going to be much more hazardous? I'm just going to finish up really by just saying a few words about risk. I've just talked about the kind of phenomena of pyroclastic flows and a little bit about ashfall, which are the hazards. But unless people are, the hazard impinges on people, then the risk is obviously varies. So risk and hazard are not the same things. Often people use the terms interchangeably, but hazard, basically risk takes into consideration the hazard. So that's the likelihood of a pyroclastic flow inundating an area or ashfall affecting an area, together with the loss. In terms of loss, the best way, the easiest way we can think of loss in all sorts of different ways. But one of the kind of simplest ways of thinking about loss is potential loss, thinking about the number of people which are in the potentially the hazardous zones. And this map just really shows us the variation in risk across the Caribbean region I've just been talking about. And you can see that in actual fact, the size of these circles is based on the number of people that live within 15 kilometers of these volcanoes. So they're within the hazardous zone areas that might be impacted by the pyroclastic flows or impacted by ash fall, for example. So you can see that although it didn't form a major eruption in the 70s, in actual fact, the largest population in terms of proximity to the volcano is actually on the island of Guadeloupe. Okay, and in terms of numbers of people close to the volcano, St Vincent, the risk is actually slightly lower. So it kind of gives you an idea, although I've talked about there being this hazard and all these volcanoes, the risk varies enormously. So just to summarize, some of the main kind of points really, pyroclastic flows are the major hazard and of course significant loss of life over the last 100 years or so in the Eastern Caribbean region from several volcanoes. Ashfall is also a major issue. I've not really focused on that so much. One of the key takeaway points is that these pyroclastic flows can be formed by a number of different mechanisms: mountain collapse, dome collapse, or lateral blast. And the risk in terms of numbers of people and proximity to these volcanoes varies considerably between the different islands. Thanks very much for listening. I'll take questions.
Thank you.
Thank you very much, Paul. Yep, we've got time for a few questions. Obviously, it is just about midday, and that's when we're scheduled to end, but we will go through those questions. First question is from Joe Mattingly. Is there something specific about the geology and tectonic setting of the Eastern Caribbean that means lots of these eruptions last weeks, months, years, in contrast to Earth's hours and days or weeks in other parts of the world?
Okay, so it is interesting that one of the things, as I highlighted the issue where there was an eruption in St Vincent the day before a major disaster in Martinique. Now, interestingly, the eruption which has just started in St Vincent, Montpellier is also showing signs of life at the same time, and that cannot be a coincidence. So there may well be some kind of tectonic link, despite the fact that these volcanoes are 200 kilometers away from each other. There may well be something about the tectonics that there is some kind of linkage. We don't know what it is, but there does appear to be some kind of linkage. It cannot be solely coincidental.
And what about the duration of the events then? Is there something special about the Eastern Caribbean as opposed to, I don't know, Italy or something like that?
No, I mean, the problem is that we don't have enough of these events. We haven't seen historically enough of these events to know how long they go on for. And I think in terms of Montserrat, it lasted 15 years. It may well be that if we saw hundreds of these eruptions, that we're able to observe them, we may find that perhaps Caribbean eruptions go on for much longer. But I don't think there is a typical length. It used to be, prior to the eruption in Montserrat, it was thought that West Indian eruptions were very brief and short-lived. Now that doesn't seem to be the case. I think it's simply we haven't observed enough to know what the normal picture is.
Okay, great. Thanks, Paul. At the moment, I don't see any further questions. It is midday, as I say. So unless any questions come up in the next minute or so, let me just say thank you to all the speakers. Great talks covering flooding, volcanoes, earthquakes, and landslides, something for everybody, really highlighting the significance of geohazards and how we can monitor and understand them. So that's great. Thank you to Sean for helping organise things. And of course, thank you for you, students and staff from schools in the region to coming along. And have a restful Easter break, which is upon us very shortly. I'm sure particularly teachers deserve that. And just to say that this year we've obviously put this event on as a virtual event, and we would like to return to a face-to-face event or some hybrid between the two. So we will be planning something for January, February 2022. Let's hope we can meet in person back at the University of Plymouth. So yeah, thank you to all those people who provided thank yous, and have a great rest of the day, and hopefully see you in 2022. Bye-bye.